In part 1, we introduced the kinematic equations. When you are first learning these, it can be a little overwhelming. You have the change in position, the initial velocity, the acceleration, the final velocity, and the time. It's a lot of variables. With 3 equations and so many variables, how do we know which ones to choose when we have to solve a problem? The best advice is to stay organized. I'm going to show you a trick that'll help you keep things in order and maybe help you solve some problems. Here we have the 3 kinematic equations. They are set up in a grid, with each column going to be different variables. The idea behind this grid is to help you choose which equation to use to solve a problem. Notice this first equation, we have a final velocity, an acceleration, a time, and an initial velocity. However, there's no delta D, no change in position, so that box has been blacked out for us. The second equation, we're missing the final velocity, and the box has been blacked out. And the last equation, the timeless one, the time box has been blacked out for us. To show you how to use the grid, I'm going to give you a couple example problems. Here we have a car initially traveling at 18 meters per second when it hits its brakes for 1.5 seconds. And it has an acceleration, we're told, of negative 2.3 meters per second. So we want to find the car's velocity after 1.5 seconds. To solve part A, I have to figure out what I know. The initial velocity is given to us at 18 meters per second. The time that takes place is 1.5 seconds. And the acceleration, we're told, is a negative 2.3 meters per second squared. If we look up at our chart in the grid, I know VI, so I put a check mark. I know the time, so I put a check mark. I also know the acceleration. But the problem is asking us to find the final velocity. I don't know that one, so I'm going to put a question mark. If we look at each of these rows, we notice that only one of the rows is completely filled out. That's the equation we want to use. So I choose the first equation. VF is equal to AT plus VI. Now I'll plug in some numbers. So I have a negative 2.3 meters per second squared times 1.5 seconds plus the initial velocity of 18 meters per second. When I plug that in, I get 14.6 meters per second for my final velocity. Now, this indicates that the car slowed down. Since we know the acceleration is negative and the initial velocity is positive, they're opposites, so we should get a smaller number. The car did indeed slow down. Now, to solve part B, I'll start once again by writing what I know. In this case, we know VI is 18 meters per second. The time still is 1.5 seconds. And the acceleration is still slowing us down at negative 2.3 meters per second squared. But this time, the change in position is what we're looking for. So consulting our chart, we have the time, check, check. We have the acceleration, check, check, check. We have the initial velocity, check, check, check. And we're looking for delta D. So the only one of these that is filled all the way across is the second one. That's the one we're going to use. I begin by writing down the formula I'm going to use. Delta D equals VIT plus 1/2 AT squared. And then I plug in my numbers. So I have 18 meters per second times 1.5 seconds. I'm going to add to that 1/2 of my acceleration, negative 2.3 meters per second squared, times 1.5 seconds, all squared. If you calculate all this, you'll find that our car traveled 24 meters while it was braking. Let's do another example to show how to choose which equation. Here we have a second problem. A car initially traveling at 22 meters per second when the driver sees a stop sign. The driver then slams on his brakes, giving the car an acceleration of negative 2.8 meters per second squared. If the car comes to a complete stop at the intersection, how far did it travel while it was braking? First, let's write down what clues we have from the problem. We know the initial velocity is 22 meters per second. We know that the acceleration is a negative 2.8 meters per second squared. So it slowed down. We also can infer from what's given that the final velocity was 0 meters per second. It came to a stop. We don't know the time, and we don't know the distance. Of course, for this problem, we don't need to know the time, so we can ignore that. So let's go through our grid. Initial velocity, check, check, check. Acceleration, check, check, check. VF, even though it's 0, we do know it, so check and check. So delta D is the only thing we're looking for. So you see how the last row is the only one that's fully filled out. So this is the equation we're going to use. VF squared is equal to VI squared plus 2 times the acceleration times the change in distance. Now if I solve this for distance and did some algebra, delta D would be equal to the square of the final velocity minus the initial velocity squared, all divided by 2 times the acceleration. If I plug in some numbers here, I have 0 squared minus 22 meters per second squared, all divided by 2 times negative 2.8 meters per second squared. Now, if I plug all that into my calculator, I find that my delta D, the distance that the car was slamming the brakes for, was 86 meters. I hope this grid helps organize your thoughts and maybe makes all these problems easier for you to solve.